here's a title, 3 formats for a PID controller, which of course is the most used controller in industry. This can be found, well, actually a discussion of this can be found in chapter 9 of my book, Control Systems Engineering: A Practical Approach. Now, the most common form, or the form that we're most used to at this stage of the game, is a form that looks like so. We have an input coming in, and of course that's the error signal. Okay. And there are various things that we can do with it. The first thing that we do, let me draw it on over here a little bit more for the first possibility. We run this through a proportional gain. Then we can take the error and actually integrate it. So I'm going to feed it through a 1 over s. And then feed this into an integral gain. And then the other thing that I can do, that's the P part, it's the I part, and the D part, is I take the derivative and feed it through a KD. And then I have my three different actions. This is the proportion. We sum them together. So I create a summing junction. My integral action and my derivative action. And they're added together, all of them. And the sum of that contribution from the three of them is the command signal that goes on down to the actuator. So anyway, this is a very common way to characterize or have the format for a PID controller, especially when you're learning about it, because the three different actions are very, very clear here. Another thing that may be useful to point out at this stage of the game too is these three gains here are, of course, the big problem when we're quote-unquote designing a controller is to pick out or to pick these three gains. And as you can see, they're just basically weighting gains, so you can emphasize or de-emphasize a particular action by increasing or decreasing the size of the gain. All PID controllers in the PID family have a proportional action, but not all of them have an integral or a derivative action. In fact, if Ki and Kd are 0, you have what's called a P-only controller. If Kd is 0, you have a Pi controller. If Ki is 0, you have a PD controller. But in all cases, and of course, if Ki and Kd are non-zero, you have a PID controller. So all controllers in the PID family have the P part. Okay. Now, the other thing that is worth pointing out here too is that there are three constants that characterize the PID controller. Now, another option for doing this that is used in industry is the following. It's very similar to this, but it's also a little bit different. So we have the error signal over here on the left, and we feed that actually all the way through the other side. We're going to add these together here again. We integrate it like we did before, 1 over s. But now, instead of multiplying it by a constant, well, we do multiply it by a constant, but we multiply it by 1 over the integral time. That's also called a reset. There's a reason for that. And then we do the same thing we did before. We take the derivative of it, and we feed that. We multiply by the derivative time. And then we add all these, we add these other two in, just like we did before, plus. But then what we do with the result is we feed it through another gain, or a gain, KPID. So this is a gain that's going to all three pathways, I guess you'd say. And again, we have three different constants, KPID, the integral time, or the reset as it's called, and the derivative time in the third element. Three different constants, And actually, what you should be able to do is you should be able to go from one version to the other version. Okay, like for instance here, you can see if you follow the signal, and I should put a U here too to show it goes to the same place. If I follow the signal, it goes in the proportional path. It goes across and it goes through KP, and then is summed and goes on out. So if I follow what's happening with this part of the signal in the second version, it goes through, is summed, and in this part, all three parts are multiplied by KP, but this part itself is multiplied by KPID, and therefore actually what you can say is that KPID is equal to KP because the pathway from E to U for this part of it is the same. I multiply the E times the KP, or I'll multiply the E part by the KPID, and those are equivalent. If we look at the second part, the integral pathway, going from E all the way through, we multiply, well, of course, 1 over S, but we have that down here, so we're doing that in both versions. It's multiplied by KI here alone. That's all that this is multiplied by. Here, it's multiplied by 1 over TI, but then that's multiplied by KPID. So one thing that we can say here then is that, let me get some room up underneath here, is that KI is equal to KPID divided by TI. Because the same thing happens to those two signals if we look at the two different versions. And then we can actually do the same thing with the last one. The third path we multiply by S, which we do up in the other path. Then we only multiply by KD up here, that's it. But here we multiply by TD, and then we multiply by KPID. So we can also say that KD is equal to TD times KPID. So you should be able to start with one version and go to the other version, whichever one it is that you start with. The other thing that I would say here is that this is an industrial version. So when you go out into industry and you tune a PID controller or design a PID controller, you're very likely to be using this version in lieu of this version up here, which you may have used to actually learn about a PID controller. Now, the other thing that I would say is that these different constants here actually you can develop an intuitive feel for, and they actually have a meaning that appeals to your intuition, and that's why they're used in industry, especially in the process industry. Okay, now there's another version that is useful too, and again it has three constants, and what it is, excuse me, of course we always start with the error signal. Oh, I'm off my camera, let me pull it down. So we always start with our error signal. And then excuse me, I'm looking it up because I never use it, hardly. We feed it through K, so a gain. And then we feed that through a first order lead. So it looks like a first order system, except that the TS plus 1 is in the numerator, not in the denominator. And then we feed it through another one, T2S plus 1. Oh, I left something out, but it doesn't matter where I put it, so I'll put it over here. We feed it through an integrator too. So actually the way that I have it in my book is I have the integrator over here, but that doesn't make any difference as far as the overall operation of the PID controller works. And what's nice about this is it actually shows the parts and pieces, especially if you're used to doing frequency response. This is your gain. And then, like I said before, we have a first order lead. and we have a first order lead again, and then an integrator. We always, with the PID controller, if you have an I part, you're going to be putting a pole at the origin, and that's what this integrator is it's a pole at the origin. And then the other thing that's clear with this too, or sort of clear, we can actually modify this a little bit, and I'll do it in just a second. We're putting in a gain, and we're putting in two zeros, basically. We're putting in two first orders that are in the numerator. They're leads, not lags. And then we're putting in an integrator too. So, if we look at that, let me pull it back up here so we can see it. I can modify this a little bit. Our GPID for this version would be K times T1S plus 1 times T2S plus 1 over S. Or we can do a little bit of manipulation here. PID equals, I'm going to pull the T1 and the T2 out, so we can have a K times T1, and then this will be times S plus 1 over T1, and then T2 times S plus 1 over T2. And then that whole thing over S. Or, continuing on with this, GPID, let me just gather our terms here. K, T1, T2, S plus 1 over T1, S plus 1 over T2, and then the whole thing over S. So the other way you can look at this, here we have it as a gain times two first order leads over an integrator, a pole at the origin, or these are zeros, and so our zeros, because they're in the numerator, and therefore we have a 0 at negative 1 over T1. That's the quantity that will make this go to, of S, that will make this go to 0. And we have a 0 at minus 1 over T2. So you can look at it as a gain, and then this is a 0, it's another 0, and pole at the origin. Now all of the other examples too have this feature. Let's do it. Do one example. I'll tell you what. Let me get another piece of paper. If we look at our original PID, so GPID, the form that's KI, KP, KI, and KD. What we have is that's going to be KP plus KI over S plus KD times S. And then if we do a little bit of manipulation here, GPID is equal to KDS squared plus KPS plus KI all over S. So we've simply collected them all with over one common denominator. And so we have a second order in the numerator, which means we have two zeros. Any second order is going to have two roots, and so the roots of this are going to be the two zeros. And then also times a gain over a 0. So, you know, you get the same result that you got with the previous case, except, with one exception, these are real roots, these two here and these two here, and there's nothing to say or indicate that these roots have to be real. In fact, those roots could be complex, so you could actually have complex zeros in a PID controller. So anyway, all of these forms are translatable from one to the other, and you should be able to know or be able to make the conversion from one to the other. What I would say about this form that I did here, the third form that we covered, is this is a nice form if you're going to do pole zero cancellation, because you can see the zeros very clearly, and if you want to cancel poles with those two zeros, or here, you can it tells you exactly what T1 is going to be. Okay, that's all, folks. That's all for now. That's all, folks. That's all, folks, like you used to see in the cartoons from the old days. Thanks for watching.